Welcome to Lecture 4.6, Phase Portraits with Complex Eigenvalues. Okay, I want to start with a lemma. Now the word lemma means mini theorem, so it's a neat little result that's going to be useful in the remainder of this lecture. So let's suppose that we have a homogeneous system, a prime equals ax, and we have a solution, x1, and let's write this as solution is complex valued, and let's write this into its real part, u, and its imaginary part, I times w. So if this thing solves our system, x1, then I claim that u solves the system and w does as well. So if we have a solution to this system, then both the real part and the imaginary part, with or without the I will work, are going to solve the system. Okay, so let's see why this is. So as before, we're going to show that this works by plugging this thing back in to the equation. So let's take the derivative first. x1 prime equals u prime plus I w prime. So that's the left-hand side. So let me say that. This is the left-hand side. And now the right-hand side of this equation is a times x1 prime, which is a times u plus iw. So this is a times u plus I times a w. Okay, so because x1 solves this equation, that means x1 prime equals ax1 prime, or ax1. So these things have to be equal, which means that this has to be equal to that. So let me circle that. So these things are equal. And again, we're assuming that u and w are real valued. I didn't say that, I didn't write that down, but let me add that, say that. So if we want to equate these two, things, we have to equate the real parts and the imaginary parts both. So let's equate real and imaginary parts. And that means, okay, so the real part of this is u prime, and the real part of this is au. So that means that u prime equals au. This is the real part. And the imaginary part up here is I times w prime. Let me use blue again. I times w prime. And that better be equal to the imaginary part of this, which is I times AW. So this is the imaginary. And so of course we can divide through by I, and we can conclude that W prime equals AW. And so thus U prime equals AU, and W prime equals AW. And that's exactly what we had to show, that U and W both solve this as well. So remember this is going to be useful in the remainder of this lecture. Okay, so here's an example of a system when our eigenvalues are complex. So this is x prime equals a times x, and this matrix, we've actually seen this before. We computed the eigenvalues and eigenvectors of this when we first learned about eigenvectors a few lectures ago. If you've forgotten, that's fine. You can either recompute them by hand or you can plug them into a computer. Either way, the eigenvalues and eigenvectors are these things right here. Notice that these things are complex conjugates, as are these things, and that's always the case. So the general solution we already have. It's c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2. But as before, like what we saw second order differential equations with constant coefficients, and the roots of the characteristic equation were complex, we had our general solution in terms of complex exponentials, but we prefer to write that in terms of sines and cosines. And that's exactly what we'll do here. So to do that, we have to use Euler's equation, and let's recall what that is. So Euler says that e to the I t equals cosine of t plus I sine of t. Okay, so here's what we're going to do. I'm going to call this x as before. I'm going to call this x1 of t. I'm going to call this x2 of t. Okay, so x1 of t, I'm going to pick one of these. Doesn't really matter which one. So x1 of t is e to the negative 1/2 plus I times t, 1I. And now I'm going to write this. I'm going to write this as e to the negative 1/2 t times e to the I times t times 1I. Of course I can do that. I'm breaking off, this is the real part and the imaginary part. And now I'm going to apply Euler's formula to the imaginary part, or the complex, the exponential with the imaginary exponent. So applying Euler's equation, I get e to the negative 1/2 t times cosine of t plus I sine of t times 1I times this vector. Okay, so now what do I want to do? I can write this as, I can move this all in. I can write this as, move this whole thing inside of the vector, and I get e to the minus 1/2 t cosine of t plus I e to the minus 1/2 t sine of t. And at the bottom I get, so I'm going to put, well, yeah, let's write this as I times e to the minus 1/2 t cosine of t. And then I have I times I here, so that's going to be minus e to the minus 1/2 t sine of t. And what I want to do now is I want to break this into real and imaginary parts. So I'm going to write this as some real valued function plus I times another real valued function. So the real part here is that and that. So let's put that in this first vector. So this is e to the minus 1/2 t cosine of t, and then this is negative e to the minus 1/2 t sine of t. And then the imaginary parts, that's going to be this and this. So I factor out an I, and then I'm going to put, so the top here I'm going to put e to the minus 1/2 t times sine of t. I'm putting this thing right here, and then I'm going to put this thing down here. So down here I have e to the minus 1/2 t cosine of t. And so this, I'm going to think of this, so this is x1, and let me call this u, let me call this u of t, and let me call this plus I times, I call this W of t. W of t. Now recall our lemma from the previous slide. If x1 solves x prime equals ax, and x1 is, if we write this into its real part and its imaginary part, then this solves the system, as does that. So therefore, we can say that by the lemma implies that u and w solve x prime equals ax. So why is that nice? Well, u and w don't have any imaginary numbers in them. They are real vector valued functions. And what else is nice? Well, we know that our general solution is c1 times x1 plus c2 times x2. All we need for a general solution are two distinct functions, and then we have the general solution. So what this means is that the general solution is, instead of writing it like this, we can write it as c1u of t plus c2, that should be let's make that more of a plus that more of a t, c2w of t. Let me actually write out what this is. So this is c1 times e to the minus 1/2 t cosine, make sure that looks like a negative sign, cosine of t, negative e to the minus 1/2 t times sine of t plus c2 times w, which is e to the minus 1/2 t sine of t and e to the minus 1/2 t cosine. Let me box that. So, I think you can still read that. So the big idea here is, instead of this general solution involving complex exponentials, alternatively, we can convert this into a solution like this that involves real valued functions. And this is preferable, and this is what I want you to be able to do. Now let me mention that you've actually seen something like this before. So let's recall in the one-dimensional case, or when I say one-dimensional, I mean when we don't have a system, when we just have a single ODE. So let me put this up here. Recall that if we had, so suppose we had an ODE y double prime plus p times y prime plus q times y equals 0. And we got that characteristic equation, and then say we got that r equals a plus or minus bi. Then we have two solutions. We have solutions that are, well, let me just write down one of them. Then we have a solution x1 of t equals e to the a t times e to the negative I b t. Actually, let me make this one plus. Say e to the I b t. That's a solution. And then we took this and we wrote e to the a t times cosine of bt plus I sine of bt. Okay? And then if we want to, this is not what we did before, is we wrote x1 like this, and then we wrote x2 the same way, and the only difference is we had a negative sign here. Then we added them together to get a solution. These things would cancel, and we subtracted them together to get another solution, and the cosines would cancel. Here's another thing that we could have done instead of that. We could have just taken x1, and we could have written it like this, and then we could have written that into its real and imaginary parts. So we could have written this as, say, e to the a t cosine of bt plus I times e to the a t sine of bt. We could have done that, and we could have called this thing, we could have called that u of t, and we could have called that thing w of t, and we could have written this as u of t plus I times w of t. And then our lemma, though on the previous slide, though it was for systems, it works exactly the same way if instead of a system, if we had a first order or second order equation. It's easier to show that u is a solution to this and w is a solution to this. So we could have written our general solution, instead of using complex exponentials, as using, let's go down here, C1, let's just say it, C1u plus C2w. And in fact, that's what we got. We just did it a slightly different method. We wrote x2 out and we subtracted them and added them. But the same technique could derive the same alternative general solution, not just for a system of ODEs like this, but for when we had second order equation and we had complex exponentials. Okay, so let's plot the general solution. And let me write this as, so let me call this u of t, like we did in the previous slide. And let me call this w of t. So u of t, this is a vector valued function. Let's say it's u1 of t, u2 of t. So it's actually two functions. And this is e to the minus t over 2 cosine of t, and e to the minus t over 2, I should say negative. Let me make sure this is negative so you can see it. Negative sine of t. And then w of t is really two functions, w1 of t, w2 of t, which is e to the negative t over 2 sine of t, e to the negative t over 2 cosine of t. So u and w really are vectors with two functions. Okay, so how do we plot what these things are? We're going to take a similar approach to what we did in the previous lecture. We're going to do some easy cases. Let's see what happens when C1 is, so let's make C1 equal to 0, and let's make C2 equal to 0, and see what happens. So let's say that C1 equals 0, and then C2 equals 1. In that case, x of t equals w of t, which is e to the minus t over 2 times sine of t cosine of t. And then the other case is, suppose that C1 is 1 and C2 is 0. In that case, x of t is u of t, which is e to the minus t over 2 times cosine of t negative sine of t. Okay, so what do these functions look like? Let me draw the phase portrait plane, or the x1, x2 plane. So this is x1, this is x2. So I claim that this is a curve, this is just a circle that goes around clockwise, and this thing is as well. And so what this does, e to the minus t over 2, this is going to go to 0, so it's going to cause this circle that goes clockwise to spiral inward. And same here. Okay, so maybe that's something that you're not quite comfortable with as to why this is a circle. So let's recall vector calculus. This is something that you should have seen then. Let me come up with do an example. So suppose you had a function like this in vector calculus. You would usually write it as cosine of t sine of t. So instead of writing it vertically like this, we write it like this, but it really doesn't make a difference how you write it. That should be sine of t. So this on the unit circle this is a path. So picture like a bug that traverses the xy plane according to this. So at t equals 0, actually let me not write it like this. So at time equals 0, we are at cosine of 0, sine of 0, which is 1, 0. So at t equals 0, we are right here. So this is t equals 0. At t equals pi over 2, we're at cosine of pi over 2, sine of pi over 2. That's 0, 1. So this is t equals pi over 2. And then at t equals pi, we're at cosine of pi, negative 1. Sine of pi is 0. So that's over here. So this is t equals pi. And then at t equals 3 pi over 2, we're down here. So this represents a circle that starts here and it goes around that way. So let's do the same thing for these two functions. For this and this, let me give these different names. Let's say this is gamma 1 of t equals sine of t cosine of t. And let me call this one gamma 2 of t. Okay, so gamma 1, so this thing at t equals 0 is going to be at sine of 0, cosine of 0, which is 0, 1. So at time equals 0, we're going to be here. So this is t equals 0, and this is gamma 1 of t. Now at time equals pi over 2, we're going to be cosine of pi over 2 is 0, sine of pi over 2 is 1. So we're going to be here. So this is t equals pi over 2. And this should be enough for you to just finish it, that it's a circle going in that direction. Now another way to see it is it's like this function. It's like this path, where this is the x-axis and this is the y-axis is up here, but we just switch the value of x and y, so it's like so swapping the value of x and y corresponds to like a reflection across this line. So it's going to take this circle to one that goes the opposite direction. So I'll let you check. Well, I'll do a little bit for you. That over here, let's check the first few points. Let's draw this curve. So this is a curve that starts at cosine of 0, sine of 0. So that's 1, 0. So this curve is going to start right here. And then at t equals pi over 2, we have cosine of pi over 2, which is 0, and negative sine of pi over 2, which is negative 1. So at t equals 0, we are here. At t equals pi over 2, we're here. T equals pi over 2. And so we have a path that goes, it's a circle, and it goes in this direction. Okay, so let's over here, this is going to be, now let's plot w and u over here. W is going to start at that same point. It's going to start at 0, 1, because w of 0 is 0, 1. So let's do say this is, so this is let me just draw this as 0, put a 1 there. So we're going to start here. And this path is going to be going clockwise, but this is an exponential, which is going to 0, so that's going to kill this circle and make it into an inward spiral. So we have a path that goes like this, but is going to very quickly die out into a spiral. And it goes in this direction. And now let's plot u. So u of 0 is going to be cosine of, this is 1, cosine of 0, negative sine of 0. It's like here, it starts right there. So u, let me draw this. This is w of t. Is that, yeah, so this is w of t. U of t is going to start at 1, so this is 1. U of t is going to start here, because again, u of 0 is 1 times 1, 0. And it's also going to go in the same path, and it's also going to be a circle that quickly dies and becomes a spiral. Now these curves can never intersect, so you can tell that u and w are going to have to be in the same direction. And now it's actually easier to fill in the gaps in this thing than it is when we had real eigenvalues, because there's not much to do. Let's take the curve that goes through that point. Well, that's going to be a circle, and that's going to spiral, and there's not much choice. So we just sort of fill everything else in. We don't have to do very much of this. I think if we just draw 1 or 2 of these, we should have the whole thing, but this is what all the solution curves look like. So this is the phase portrait. Now something else we can do here, and this is something that we could have done for the real eigenvalue case as well. We just didn't, but we can draw the component plots. It's especially helpful here. So I'm going to call these component plots. Component plots. So what I mean by component plots is, so u and w are functions, and so this is the function, u1 and u2 are functions that we can plot as functions of t. So u1 is this, u2 is this, w1 is this, and w2 is this. So it's not too hard to plot these things. You can use a computer. I'll just tell you what they are, and then we'll explain why they are what they are. So this is going to be, so w1 of t looks like this. u1 of t, this is 1, is going to look like, I'll use a different color. May not be exactly the scale, but it's close. So this is u1 of t. u2 of t is going to look something like this. This is u2 of t. And I could plot, I'm not going to plot w2 of t, that'll just get too messy. Now I'm not too worried about the intercepts. I worry more about qualitatively these things. Think about this. The u1 is a cosine wave that is killed by an exponential. So a cosine wave is normally going to look like this. It's going to normally look like this. But if it gets killed by an exponential, it's going to die off quickly and look like that. And u2 is a sine wave, negative sine wave. Normally that would look like this, but it's getting killed off by an exponential, so it looks like this. So think about what these things mean in terms of here. So u1 is, so u1 and u2 has a meaning in terms of this blue function. So suppose there's an ant that's following along this path. So right away, the ant starts here, and u1 of t measures how far the ant is from the y-axis. It's the x1 value. That's the u1 is the x1 value. u2 is the x2 value. It measures how far we are from the x1 axis. So as we're going down here, you can see that the x1 value is positive from here up to here, And then the x1 value becomes negative. The x1 value becomes positive, negative, positive, negative. So we're just measuring the distance of the ant along the blue path from the y-axis. Conversely, so u1 starts positive, becomes negative, and positive. Similarly, the u2 value measures how far we are above or below the x1 axis. So that starts negative, 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 positive, 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 negative, 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 positive, and that's u2. So it starts negative, becomes positive, becomes negative, and so forth. So I encourage you to, to try this on your own. And I'm missing one of them. I'm missing w2 of t. Try plotting that up here. So the last example in this section is when we have purely imaginary eigenvalues. So consider a system x prime equals a times x, and here's an initial value. So this is an initial value problem. It's not hard to compute the eigenvalues and eigenvectors of this. It's elementary, though I don't want to spend time in this section doing that. I want to instead assume that we know what they are and then spend time analyzing what that means about the system. So here are the eigenvalues and eigenvectors. Right away we know the general solution is x of t equals c1 e to the lambda 1 t times v1 plus c2 e to the lambda 2t times v2. So as before, I'm going to call this thing x1 of t. And I'm going to call this thing x2 of t. And as before, I'm going to take I can take either x1 or x2. It doesn't matter. Let's just take x1 because 1 comes before 2. And I'm going to write this into its real and imaginary parts. So x1 is e to the 3/2 it. So I'm going to use Euler's formula to write that as cosine of 3/2 t plus I sine of 3/2 t times the vector 5, 2 minus 6i. And now let's write that into its real and imaginary parts. So this is, okay, so the real part on top is this cosine term times 5. So let's write that as 5 cosine of 3/2 t. And then the bottom, the real part, is going to involve, so this times this is going to give us 4 terms using the distributive law. So 2 times that is going to be a real part. So let's write that down. That's going to be 2 cosine of 3/2 t. But we're also going to have a real part from this I sine of 3/2 t times negative 6i, because I squared is negative 1. So that's going to be plus 6 sine of 3/2 t. So that's the real part. Now the imaginary part is going to be plus I. Let's do the same thing. The imaginary part up top is easy. That's this thing times 5. So that's going to be 5 sine of 3/2 t. I hope I left myself enough room on bottom. Imaginary part on the bottom is going to be 2 times this. So that's going to be 2 sine of 3/2 t. So 2 sine of 3/2 t. Yeah, I should have enough room. T. And then we also have, is it plus or minus? Let's see, we have negative 6i times cosine. So that's going to be negative 6 times cosine of 3/2 t. Minus 6 times cosine of 3/2 t. And the I, of course, is outside of this. So I'm going to write this as, so I'm going to call this u of t, and I'm going to call this w of t. So x1 we've written as u plus I times W. So the general solution, so it's right up here, the general solution, I'm going to save myself space to do the face portraits on the bottom. General solution is x of t equals c1 times u, so which is, let's just write that up, 2 cosine of 3 halves t plus 6 sine of 3 halves t. And on the top we have 5 cosine of 3 halves t, and then plus c2 times the bottom is going to be 2 sine 3 halves t minus 6 cosine of 3 halves t, and the top is going to be 5 sine of 3 halves t. So again, this two-parameter family of solutions involving complex exponentials gives us exactly the same set of solutions as this two-parameter family involving sines and cosines. Now that is if we allow these constants to be anything, real or complex. So one thing to notice is that this is different from the previous example because there aren't any exponentials in there. Remember the exponential e to the at came from the fact that we had lambda having a real part. Lambda equals a plus bi, and if we just have an imaginary part, then let's just remind you, before we had e to the a plus bi, which was e to the, maybe let's say a plus bit, which is e to the at times e to the bit. So in the last example we had this thing, and a was negative, so this we wrote into sines and cosines, and then this thing killed off those sines and cosines because a was less than 1. Okay, so let's plot. Let's do the face portrait. So how do we do that? Let's plot the one curve that actually satisfies this initial condition. So let's use the initial condition. So let's say that x of 0 equals, okay, so we got to plug in 0 into where again? We got to plug 0 into here. So if we do that, you know what, you can also plug it into here. It actually really doesn't matter if you plug it into here or if you plug it into here. And this actually might be a little bit easier, so let's do this. So x of 0 equals c1 times 1 times 5 minus is that what I want to do? Now let's plug it into here. It's going to be easier. Yeah, so plugging 0 into here is going to be c1 times 5 times 1. So that's 5 on the top. And on the bottom we're going to have 2 times 1 plus 6 times 0. So 5, 2 plus, technically I should have called these constants C1 and C2 something different than these because they aren't the same C1 and C2. I should have called these like D1 and D2, but I think it's fine. Okay, so plugging in 0 into here, we get 5 times 0, that's 0. So C2 times 0. And then the bottom, we're going to get 2 times 0 minus 6. 6 times cos. So that's going to be, that is a negative 6, right? On the bottom. Yes, so we have, so plugging in, is that correct? Yes, that's correct. Okay, so this is, we set this equal to -1 and -2. So this is a system of equations, and it's something we can solve either by hand or we can solve using a computer. I'll just tell you what the solution is. It's not hard to see that C1 is negative 1/5, because this thing is saying 5 times C1 equals negative 1. So C1 equals negative 1/5, and C2, this is a little harder, but it's just algebra. It's 8th or 9th grade level, is 4/15. So what that means is this particular solution happens when C1 is negative 1/5 and C2 is 4/15. And that happens, I was thinking if I'm going to have enough room to do this. So x of t, so if you plug negative 1/5 into here and 4/15 into here and you simplify, I'll just tell you what you get. You get negative cosine of 3/2 t plus 4/3 sine of 3/2 t on the top, and on the bottom you have negative 2 cosine of 3/2 t minus 2/3 sine of 3/2 t. Now it's not clear what this thing is. It turns out this is an ellipse, and it's an ellipse through this point right here. So let me sketch the face portrait. We're not going to have much room, but negative 1, negative 2 is going to be about there, and it's not clear to me how to know exactly what the major axis, the minor axis is. So this is something that you are welcome to use a computer and figure out what ellipse this is. And turns out that it looks something like this, and it goes in this direction. Now you should be able to figure out what direction it is just by plugging in some small values of t by hand and seeing what points those are. But now our general solution does not, our general solution and this particular solution does not have an exponential e to the at attached. So this is not going to be a spiral. It's not going to either shrink or grow like it would if there were an exponential. And that is because the eigenvalues are purely imaginary. So the phase portrait, I should probably label my axes now, is going to x1 and this is x2. These are just going to be conocentric ellipses. And so the particular solution satisfying this is going to be the one that goes through the point. Let's say this is negative 1, negative. So this is negative, I'll just say that's negative 1, negative 2. And these things are going to be going in this direction. And we can also plot the component plots of this. So this is x. So let's plot x1 and x2 of t. So this is x1 of t and this is x2 of t. And we can actually plot these. Again, I would use Wolfram Alpha or your calculator. It's not at all clear what this thing looks like, other than the fact that it is some sort of sinusoidal curve. And it turns out that x1 looks like this. This is x1 of t, or x1, I mean this, and then this thing here, x2 of t, turns out that has a little bit higher amplitude, and it looks sort of like this is x2 of t. And that's just a sketch. I encourage you to pause this video and plug these into your computer or calculator just to see what they look like yourself. Okay, so let's recap what we've learned so far. Suppose that we have a system of ODEs, homogeneous system, A prime equals AX, where our eigenvalues are complex numbers. And let's assume that B is non-zero to assure that they really are complex and not just real numbers. So we have two solutions. Let's assume V1 and V2 are the eigenvectors. Then our solutions are e to the lambda 1t times V1 and e to the lambda 2t times V2. So let's take one of these solutions, either one, and use Euler's formula to write it into its real part and imaginary part. Because we don't like writing our general solution using complex exponentials. So If we do that, then the general solution, instead of using x1 and x2, which we could have done, is c1 times u plus c2 times w, and these involve real-valued vector functions. Now the face portrait will have ellipses. Circles are special types of ellipses, but either way, these will have ellipses, and these ellipses will be spiraling inward if a is less than 0, and spiraling outward if a is greater than 0, and they'll be stable if a equals 0. And the reason why is because, let's recall where that came from. If we have e to the a plus bi times t times some vector, let's say, I don't know, some vector or something like that, we write this as e to the at times e to the bit times our vector. Let me actually call this something. Say this is, I don't want to use AB, let me use x1, x2. And then we use Euler's formula to write this as e to the at times cosine of bt plus I sine of bt times x1 and x2. And let me emphasize x1 and x2, these are numbers. This is like 2 and 6 or something like that. And then we move these inside and we have sines and cosines. This thing is going to be an ellipse, this curve. But then this is the thing which is going to either kill this ellipse off to 0 if a is less than 0. For example, if a is less than 0, we might have e to the minus 1/2 t, which is going to go to 0 as time goes infinity. Or if a is greater than 0, we might have e to the 1/2 t, and that's going to go, let's say that's going to go to infinity as t goes to infinity. And if a is 0, then this just becomes 1, and we have just ellipses, and it's not going to spiral inward or out.